From the MIT Energy Initiative, this is What If It Works, a podcast looking at the energy solutions for climate change. I'm Kara Miller.
And I'm Rob Stoner.
On today's show, a glimpse into the future of nuclear energy. Of course, nuclear power plants have been with us for a long time, and they produce a lot of energy. But traditional nuclear energy comes from fission. And for some scientists, an enormous source of excitement is fusion, a type of nuclear energy that could change our lives. How? Well, think about it this way.
There are only two effectively inexhaustible sources of energy on Earth. It's the heat content of the Earth, which is what we call geothermal, and it's fusion. It's fusing together the things which are in water, the heavy forms of hydrogen.
That's Dennis Whyte, a professor in the Department of Nuclear Science and Engineering at MIT, and he's the former director of the MIT Plasma Science and Fusion Center. He says, unlocking either the heat content of the Earth or unlocking fusion would be totally game-changing, and not just scientifically.
Access to energy is the most important geopolitical aspect of leadership right now in the world. And in fact, it's also the greatest source of conflict, as we also see around on those things. And both of those have interesting aspects to them, that namely, that's the science truth of them. And then the reality of them as practical energy sources is that they're both technology driven, where we, the United States, have an obvious advantage about being able to do that because we won more or less all of the major technical races of the last 50 years. We could win these ones as well, too. And I think that would be really important, not just to the United States, but to the world.
But why should the government and companies and institutions spend money on fusion if the fusion's still in development, especially since solar panels and windmills are out there in the world working?
So the first answer is math. We are using exactly the same percentage of our energy sources in the world come from carbon-based fuels as they did 10 years ago, as they did 50 years ago. And so that's the math of it. So people are confused by this. People see wind farms, they see solar farms, and they go, well, we must be getting greener sources of energy.
Right.
Worldwide, we are not.
Why not? Whyte says the answer's kind of stunning.
I have a chart which basically shows the energy mix has barely moved. My plug was like to 1970. So like 50 years ago. This is good because, we can kind of realize this is within our lifetimes. It's like, it hasn't moved. But the worldwide energy production has almost tripled. So if you were to poll most people, like yourself, you just go, are we emitting less or more carbon now into the atmosphere than we were 50 years ago? We think of our big gas guzzler cars, the ones that our dads drove, the big Chryslers, and all the smoke coming out. We're way less. It's triple what it was 50 years ago.
Not only are there more people on the planet than there were 50 years ago, but more of those people are living energy-hungry lives.
In general, I think we are not deluding ourselves, but we're feeling better about ourselves by deploying things like wind and solar, which are making some difference, but it's barely keeping up with the increase in energy demand worldwide. So when we say things like, well, don't build more coal power plants, country blank or something, we've got some chutzpah, I have to say, is in terms of the West. To me, it's a moral issue. It's like, how can we tell you not to deploy energy when we got rich and wealthy by using these energy sources ourselves? And it's like, now we're saying, oh, no, you're doomed to poverty because we're not going to let you actually use energy. So I'm a scientist and people don't think of me as a philosopher on these. I feel energy is the moral issue of our time. And it's because energy is linked to human well-being because it's linked to economic well-being. And by denying people access to clean energy, it's a moral issue.
So if about 80% of our basic energy comes from burning fossil fuels, Whyte says, you need an energy source that is usable on demand, that's scalable. And creating such a source is not a problem that's easy to solve.
So right now, even if I just came along with a magic solution that can provide carbon-free electricity at arbitrary levels, we still can't use it, actually, because our electrical grid could not tolerate the ability to actually transmit that much more power. And what I mean by use it, right, is we just replaced all liquid fuel transportation with electric vehicles now. The grid literally cannot operate because you don't have the transmission capabilities. And there's a subset of people who make arguments that we have all of the technologies now to decarbonize. In my opinion, that is false. We actually do not have the technologies. And what I make it clear here is that fusion is one of those things which is driven by technology, which we should try to do because it has the features of what I just said, right? That it is carbon-free, it's intense, and it's on demand. You can't change that part of renewables, which I'm not against renewables. It's just that they're part of the solution. It's extremely unlikely from a science point of view that they're going to be the total solution.
So let me just qualify a little bit what you said for our listeners, because they'll be saying, gee, we do have wind and solar and batteries, and we do have the technologies we need. But I think what you're saying is that the scale that we would need to deploy those at is impractical.
It's impractical, particularly not only to decarbonize our electricity sources, but all the other things, which is only approximately 20 or 25% of our energy use comes from making electricity. We need things that solve air travel and long-range transportation and industrial uses of heat and all these other things. And the further you go away from electricity, also the science of renewables, of wind and solar, get worse, not better. And that's the reason they haven't been deployed in those areas.
There's this other funny thing that goes on too with the transformation of our energy system. With the expansion of electricity using solar and wind, they're inherently distributed forms of generation. They're all over the place. And that necessitates a simultaneous change in the structure of the grid. It goes from being a centralized source that's radiating outward through the wires to one that's more of a mesh.
Right.
And that's an expensive thing to do, and it's also a complicated thing for grid operators to make a system like that work optimally. One of the nice things about nuclear, whether we're talking about fission or fusion, is that like coal plants and gas plants, these are large centralized plants. We can literally drop them into the grid as the grid now is configured.
Okay, so you're saying, I get it, solar and wind, they're good, but they're not going to do it all. Is there anything else, fusion, again, it's still in the future. Is there anything else that exists right now? We could go with regular nuclear energy. There are nuclear power plants out there, and they're producing energy like right this second, and they're powering things. So why think about something that's maybe could work out and maybe won't work out?
Right. So I am fully supportive of certainly that we should keep using our present nuclear fleet as well, too. And I think we should expand it because it is a solution that is right in front of us. This will get back to my discussions about fusion. Actually, this shouldn't be Dennis Whyte's opinion about what energy use we should have, we should do. By the way, it's the other reason the 82% doesn't move. It's economics, right? If fission energy was less expensive and
like traditional nuclear,
absolutely.
Okay.
Standard fission nuclear power plants, and they met the market demands better, then they would be used more as well too. So all of that's good, and that's exactly what we should do. So fusion is interesting because it uses literally the opposite physics in many ways of what fission does, but it has features in it which are, as you pointed out, Rob, are similar, right? Is that you get really large amounts of power, you have fairly good access to fuel. It's just interesting. There's sort of more social and safety implications for fission, but those we figured out how to do those. But this also gets back to my first graph and so forth. What you have to realize, we are not solving the problem for us, for the United States. In many ways, we've got it easy. We have really quite clean air. We've got good emissions control. We have a really robust mix of different energy uses. We've got hydro, nuclear,
really cheap gas,
and really cheap gas, all those things. What we're actually solving for is how do you decarbonize a growing economy like India's? Mm-hmm. We need to provide something to them so they're not going to build more coal plants because they're going to keep lifting their people out of poverty by using energy. Like let's not use coal to do that, but they're going to keep using coal to do that.
And by the way, over the last 10 years, or maybe even less, India's gone from having something like 60% electrification to very close to 100% electrification.
Yes, and it's because of coal.
It's because of coal, and they've been very aggressively expanding that fleet, and people are living better.
So I have a question for you, Rob. When India thinks about this question of the energy mix and let's say thinks about traditional nuclear, is it all a monetary? Dennis, we're talking about the kind of economic pushback. Is there also a social pushback?
Yeah, there is. I mean, India, unlike us, again, lacks this sort of enormous amount of land that we have. And they have a very high population density. And it's hard to site nuclear power plants in the United States. It's really hard to site nuclear power plants in crowded countries. So that's a challenge for them. But I think their attraction to coal, and the same is true in China to a large degree, is that it's just so inexpensive. And when you're in a poor country and the difference between having electricity and not having electricity is money, that's a powerful driving force.
Yeah. And then there are geopolitical consequences to the use of fission, right? Because it is the same technologies that you use to make fission work have connections to proliferation, right? Because they're linked by the science of it. Now, again, we have good safeguards in place and we do those things, but it is a complexity, right, around fission. That's certainly true.
Now, the Chinese are advancing quite rapidly in building up a nuclear fleet. It's not as big as ours yet, but it will be in a few years at the rate they're going. And that's different from the Indian situation. And it's not because China's less crowded, but they've got a lot more power within the central government to make these siting decisions. There's some indication that the Chinese people are not happy about that, although they are happy to have electricity.
And is that also a question of money, that the government's just like willing to spend what it takes?
Yes, and the Chinese are very, very good at manufacturing things and carrying out large projects, impressively so. And they're able to build these plants much more inexpensively than we are here. And to some degree, they're driven toward that because they lack our abundance of natural resources. They don't have the hydro capacity that we have. They have some. They don't have the natural gas capacity that we have. Mm-hmm. And so that's driving them down a different path. And the same sort of decisions play out in different ways all around the world. The Japanese, of course, have even fewer natural resources and are forced to make decisions that would be impossible for us to make here so far. So I think, conventional, if you like, nuclear power has a role in the near term as these countries convert and build up their electricity supplies. I think what's exciting about fusion is that it enables us to open up yet another direction that is more socially acceptable, I think, in this country. And that's because of the nature of the fuel and the fact that fusion plants aren't going to produce the same large quantities of nuclear waste that our fission plants produce. And that's been a problem for social acceptance here.
Mm-hmm.
Yeah. Guess who is racing towards fusion energy? China. Exactly for the same reasons that Rob just pointed out. Because of its sustainability, it's a technology. In the end, like a fusion energy industry will have an enormous supply chain that's pushing around these integrated technologies of pushing those forward. China wants to be a leader in that, not just for its own energy use. In fact, I would believe if I was them, also for the geopolitical influence that it'll bring as well, too.
Do you have a sense of what that race between the U.S. and China looks like with fusion? Are they ahead? Or
They are ahead.
Is it like cloaked enough in secrecy that you don't really know how far ahead?
So maybe I will actually No, it's a good question, but it has like most of these, they don't have simple answers. Is that if you look at the government program of China right now and its national intent, this is ahead of the United States' national program. We do not have a national policy that says we are going to develop fusion energy. We should. Right. And in that sense of what they're doing it in a very centralized way that China can bring to these kinds of problems. They just recently announced, in fact, effectively an industrial consortium that they're going to put the whole thing, they're going to put their shoulder behind that wheel and push it. It's not just, we're going to give more money to research labs to look at fusion. We're going to employ basically all of these tools that we've built up in our industrial toolkit of steel manufacturing, of their existing nuclear industry, concrete manufacturing, the whole thing, and their stated goal is we're going to beat the West to fusion energy. So now, but you say, are we behind or ahead?
Yeah.
The one thing where we are ahead is in innovation. This casts itself into a lot of the other kinds of challenges we have around these two very different systems about how you get to the goal line. And the Chinese will have a very centralized program and put everything behind it, and they've got their act together about figuring it out, and they're very good technologists and engineers and all those things. But the U.S., I'll make it a little bit broader, like the U.K. and probably Western Europe as well too. Our system favors like inventiveness and innovation, and so that's good. And we've got companies that are trying to innovate their way to better products. It's interesting about which one will win. I'm not sure.
So this reminds me of your creation story, so to speak. I mean, talk about the government not leaning into something. When you were the head of the nuclear department here, the government withdrew funding.
Yes.
And applied it instead to a consortium called ITER that's operating in the south of France to build a reactor there, but basically withdrew their support for fusion research in the United States, in the university system at any rate.
So the government was like, yeah, we're funding fusion and research at MIT. Yeah, now we're done.
Yeah.
What happened?
Yes.
It's a little falling out with the government.
It's complicated, again, as usual. So part of it was an evaluation about where fusion was. And this is approximately 10 years ago that this decision came down. And so it's interesting. Everybody kind of knew where fusion was going, right? We should make it clear, like fusion at this point was a science endeavor. It was not about fusion energy at all, okay? And like a lot of other sciences, like in the big physical sciences, like accelerators and so forth, the general trend was, we're going to get bigger and bigger to be able to, and mean bigger projects, bigger checks that you have to write and so forth. We're going to get bigger in this. It leans towards international collaboration. And, if you sort of take CERN as a good example, in Europe or these other, or the International Space Station, these are good examples. And this is where everyone saw fusion was going, right? And so what I mean was that the next stages of science exploration, we're going to be in bigger projects, not smaller projects.
Hence the old saw that it's always 50 years in the future.
Right. And that made sense too. Here's this project that's going to take, whatever. At that point, it was going to take still 10 years to construct it. We knew this.
CERN, the big thing where they accelerate the particles
and that's the big thing that accelerates it around.
And so even physically big. Like you have
so
to
that takes all
that
that accumulates all the countries in Europe and all that. And so this was just, infusion looked like it was just sitting in that usual trend of this. So, small scale university experiments looked less and less relevant, right? Now, I can make some arguments about the fact that we weren't irrelevant, but for interesting reasons. Is that it meant, so there's some great irony in this. Like we were never really, in the end, the political reality was there needed to be budget freed up to be able to pay for these extremely much larger experiments. And we're not going to go small, right? So this wasn't about effectiveness. It wasn't about the science was any good anymore and so forth. It's just like, that's the trend and we're going to go there. So I have to say there's some great irony in this. And it's like, what is this? It's because what has happened a lot because of, not just because of what we did, but a lot because of what we did at MIT in the start of Commonwealth Fusion Systems, is that we changed the narrative that it wasn't just about science anymore, is the idea that we should actually think about making this an energy source, right? And in order to make it an energy source, you looked at these enormous international projects, and you did a quick calculation. How much would they cost per watt? Like, what's the dollars per watt? This is how you basically keep score for energy sources. And it showed it wasn't even close. I mean, it was like a factor of more or less like 100 away from other kinds of energy sources. Oh,
it was like 100 times expensive,
more expensive for the same amount of
country collaborative in France.
Yeah, so not even on a commercial trajectory.
Not on a commercial
end
trajectory.
There.
So it is. So and this is it is what it is. It's a science experiment about accessing that next level of science. So there's some great irony in this, as I always said, is that it turned out what we were doing at MIT for science reasons and to keep it at a scale that actually made sense for a university We were using a particular path which exploited access to very high magnetic fields because it was a specialty of what we did at MIT in sort of the history of MIT. And the reason we did that was to keep it intentionally very small but high performing. And in the end, it's just like, the realization that there could be a possibility of translating that into an argument for economic fusion was really what launched like the thing that changed the trajectory for MIT's fusion program, and for, I would argue, about setting us on a really valid path towards fusion as a power source. So in many ways, they have different purposes. There's also an irony in it, is that in a weird way, maybe that canceling made us think about what we were. And it made me think personally of what we were. I was in fusion to do science. I never really thought of it as an energy source. I thought the next generations will maybe do that. And then what was dropped into our lap was really an opportunity to translate our science expertise into the idea of actually making an energy source.
So wait, how did the withdrawing of funding and the U.S. government being like, it sounds like this is kind of small potatoes. We need to put our bets on, like, sort of do the big bets here. Yeah. How did that lead MIT to really a place where like this stuff is being commercialized? I mean, it's strange that the money got taken away and then things started to accelerate.
People might look at it, this was just a different way, because I know there's some critics of this. They go, you just convinced some rich people to basically give you money, like through the private sector, to keep doing your sort of science experiment. No. What it was actually, it was an internal transformation for a large part of us inside the team at the Plasma Science and Fusion Center that realized we should actually try to make an energy source. I remember the day when we said, because we worked on this plan, which is basically take our idea, high field confinement device, these high magnetic field confinement devices. We came up with a valid technical plan, but really our biggest commitment and change was thinking of ourselves as energy developers rather than just scientists. Now, obviously, there's science and technology that is behind that. That evolution was the biggest single change in my professional career. And the good part of it was to say, and we've got the team to be able to execute this, which was what we had at the Plasma Science and Fusion Center, and then eventually spinning out, in fact, Commonwealth Fusion Systems about doing that. But we were way too isolated and insulated, in fact, from the energy development world. In fact, one of the great things that we did was walk over to the Energy Initiative and actually start learning about, I'd never talked to anybody in the energy sector. It's like, we're just physicists really playing with our toys. It's like, so walking over to a place like the Energy Initiative at MIT also woke us up. It's like, holy cow. It's like, this is actually what it's going to look like. What you just said, Rob, right? Schedules, timelines, resource. And when you come with that and put yourself in that position, then it's very interesting. It still forces, by the way, amazing science. It's just that you're working towards a different goal.
Now, Commonwealth Fusion Systems, which you've talked about, which spun out of MIT, which would you say it's the leader in fusion right now?
In the private sector.
In the private sector.
Yes.
Okay, so I know it's raised money from rich people, as you mentioned before. So if you're talking to a rich person who's not a physicist, and you're like, this is why you should give us money, are you on their board of advisors, or are you affiliated with the company? No.
I have no, it's for other reasons I can explain, but I have no official affiliation with actually Commonwealth. Yes.
But let's say either you or they were like, you should give us money, rich person, to fund this. It's really very important. How would you, to an ordinary person, explain what it is they're funding and why they should do it? Yeah. What is fusion?
Right. So fusion is the fusing together of hydrogen to produce energy. So this is the same process that powers stars, our own sun as well too. It happens in the middle of the sun. In the most well-known condition for this, it has to get very hot. It has to be on Earth, it has to be above about 50 million degrees Celsius.
Now, by hot, you mean the hydrogen atoms have to have a lot of kinetic energy.
This fuel has to get hot, right? Yeah, so in the middle of our sun, it's about 20 million degrees Celsius. And this gets hot enough that it allows the hydrogen to push against each other close enough that the fusion can occur. And again, on Earth, about the minimum temperature is about 50 million degrees Celsius. And then there's a requirement that you basically have to have enough fuel around in order to create enough fusion reactions that then keeps itself hot, right? And so once it gets to that point, it becomes like a star that basically it starts keeping itself hot through its own fusion reactions. And so it as we say, even though it uses somewhat different reactions, it's basically the same thing as what's happening in the middle of a star.
And they're being these atoms are being confined because the star is a star. It's a massive object.
Exactly.
They can't get away from each other.
Exactly. So fusion only works in one place naturally in the universe. It's in the center of stars. And the reason for this is because of their enormous size. So the containment of this, like it's 20 million degrees in the center. It's only 5,000 degrees. It's like it's 1,000 times colder on the surface of the sun. How does that center stay hot? Well, because it can't go anywhere because it's contained, it's confined by the gravity of the sun itself. And gravity, as you know, Rob, gravity is the weakest of the fundamental forces of nature by a lot.
Hard to reproduce.
Yes, and it takes, that's actually why, so Jupiter is interesting. It actually has almost the same composition as the sun, but it's not a star because it's not quite big enough. So there are no really, except for some exotic examples, and there's not really small functioning stars around. So you cannot translate that directly to Earth. You need a much stronger force. And what you use is the electromagnetic forces, which are much, much stronger, in fact, than gravity. So this goes to your question about like what happens is that it turns out that the force that you're applying for the containment is that you trade off. You can keep something hot by making it larger, like a star, or in fact, this is what ITER and other things like this make themselves really, really big, and that will keep it hotter longer, or you can apply a more effective force. And that force is a magnetic force, and that comes from making this magnetic field that is produced by electromagnets. And so there's always a trade-off between large, which allows you to keep it hot, versus more force. The analogy we use is that it's kind of like keeping your home warm, is that you do it in one of the ways is to just like make it really, really big, like make the walls like super, super thick, or you improve the quality of the insulator.
Got it.
Right? And so making the magnetic field stronger makes the insulator way better, and what it allows you to do is it makes the object smaller, but still get the same containment. That was the science of it, but it turns out the economic impacts of this are staggering because fusion is a very interesting energy source. What you pay for is the thing that you build. The fuel is free and it lasts forever. What you're paying for is the containment system.
Okay.
Right. So in this particular one, which isn't the only way to get to fusion, but it's sort of that's the one Commonwealth uses and the most prevalent one right now, is you end up building large electromagnets, which make a containment cage, which hold the hot fuel. So it actually costs very little money and very little energy to get it hot. What's hard is the containment.
They want to fly apart from one another.
Yeah.
Okay. It's to keep it keep it hot continually. Okay, so then you have this very hot thing.
Yep.
But the problem isn't solved yet because like I want to power that factory down the road and I want to power my house.
Yep.
So
fusion sounds very exotic in a way. It's happening. Like this is the process that powers a star. But in the end, what happens is that the fusion, where is fusion energy? When the fusion occurs, the energy is released. It's literally in the velocity or the kinetic energy of the particles that come out. They're the same particles as before. They're just rearranged by E = mc squared. They just have an enormous amount of energy. So what you do is you stick something in front of those particles and get back the energy. And how you get back the energy is you force them. But they basically bounce around like billiard balls almost right inside of the material. And what you do is you put some engineered object, and we call this a blanket because it kind of surrounds or the fusion device, that then gets hot because those particles are forced to give their energy into regular matter and it gets hot. That's it. So fusion makes heat.
okay.
So the engineered thing that we make is heat. This is why it's so lovely. Fusion is because this is basically almost all our energy sources is what we do is we make heat with them, right? And then we do something with the heat, like make electricity, or we make fuels, or whatever the thing is that you want to do. That's actually what fusion makes in the end. So almost your vision of this is you build an object. It costs you something to build this object, right? This complex object. Then after that, the fuel is, you can just burn arbitrary amounts of fuel in the thing because it's almost for free. And then what's coming out of it is heat, That's why I get excited about ideas that I was like, how would we use fusion, not just to make electricity, but to actually get after that 82% business.
So the rich person that you're pitching this to says, when will this be powering? Like, what's your timeline here for powering homes and factories?
So, okay, it's interesting. So it depends about who the person might be. Often those people, by the way, are in the positions they are because they're technologists.
Okay.
Yeah. So to that person, I would describe what we're doing. I actually wouldn't get into the details immediately of the physics and so forth. I would just, I would look at this laptop, right?
Yeah.
Or an iPhone.
Yeah.
And I would go, you realize like they know this, right? The decades of science innovations. Like when Shockey invented the transistor, could he have imagined an iPhone, right? But you realize that these are fundamental pivot points in the understanding of the science and technology. And then you're working on these things and all that information theory, all these things. And then at some point you realize, holy cow, I can actually put this together into a product. And so all of those, and I guess most of those very rich people are there because they saw an aspect of an idea of commercializing something that just looked like science fiction at the time, right? And I would go, that's what's happening in fusion. It's like, yeah, there are details about what the technology will look like and so forth. The most important thing is that we've built now, or we've got the entities called companies, which are trying to build a product. And that doesn't sound like much of a breakthrough, does it? But it is. Because until you have that, you actually have zero chance of actually making an energy product, because who can deliver it, right? So that's what I say to them is like, so you come into this eyes wide open, understand that some of the approaches are not going to work, right? But what the goal is, it's not just fun science. It's actually to make an economically viable energy product. And when you do that, what you have is a possibility to displace a $10 trillion a year economy, which is basically the worldwide energy sector. That's the argument that you make. And they all get that. It's just like, what did Amazon disrupt, right? Retail, right? Because of the invention of the internet, right? Which they didn't do, but they pounced on that opportunity. I could just go on and on about, like, we're surrounded here at MIT by biotech. Biotech was built on decades of underlying scientific research, and all of a sudden, wow, we can edit we can edit genes, we can do these things which actually allow us to do things that looked impossible, like even 20 years ago.
And you don't just mean biotech like in labs, you mean like Merck and Pfizer and Novartis,
Absolutely.
like the companies that came out of that.
Look at what, and also to the people that go, oh, this is all going to be slow, you can't go fast. Like, again, look around where we are, right? Holy cow. Again, we got a vaccine like that fast, right? Against
COVID,
a global pandemic.
Yeah.
When we're trying to solve really important problems, we can go fast. And we go fast by innovating, by having the right structures around us. Again, imagine that we were at a place and all we had, and this isn't against government labs or anything, because curiosity-based research is absolutely critical to these kinds of things. But imagine that came along and there were no biotech companies. How long do you think it would have been? I think we'd still be waiting, actually, probably for a vaccine, because
far fewer of us.
And it's because that's what they're built to do, right? Yeah. So that's basically the argument, not just actually to the billionaires, but to us as a society, right? Isn't this what we should be doing?
So there
are these kinds of hard problems.
There's no blueprint for how you combine those developments in science and our understanding into a working fusion reactor. And in fact, there are a number of startups around the world. Last time I looked, there was something like 40 plus trying it in different ways. Tell us a little bit about the structure of that sort of global effort.
Right. It's like, I almost can't believe I'm recording this and saying there are 40 private sector fusion developers, right? This is so part of it actually comes from how would it be possible that there's 40 ways to do it? Well, this comes back, as usual, to some underlying science differences in fusion. The science of fusion allows you to access high power and high gain in just a staggering number of ways. And that's actually what these approaches are, in some sense, exploiting, but also challenging, because it's like, which one of those gets you to the goal line, which is the economic product? And so then the answer about when you get there actually becomes about how clever you become, how well you deploy the resources, and basically having a distributed aspects of many shots on goal, in fact, to be able to do that. We call this competition. We call this the market, right? And that's actually going to be the answer. By the way, not to pick on it, right? But we already have fusion. We've actually made fusion happen in the laboratory for a long time. We've actually, the experiment here at MIT in something like only like this big across was 5 times hotter than the center of the sun, right? We have experiments where we're making hundreds of trillions of fusion reactions per second. The containment is absolutely good. We've actually made fusion already.
So let me the important point there is it's not a burning plasma, so to speak.
It's not a burning plasma. And in fact, now, though, by the fact that we saw one at the National Ignition Facility, right, we actually saw that as well, too. So fusion is not science fiction. It's not about that. Like, we already made fusion. What I'm talking about, when will we have fusion energy systems?
Like the commercialization.
Yes.
But is this like, give me a sense. Are we talking like 10 years,
Yeah.
4 years? Like what's the scale,
What's the scale
people should be thinking
what you
about?
can do that, right? So then that goes to the specifics of each of those kinds of approaches, right? So I can speak to the one, so what we did was we looked at the scenario and said, okay, what would it, and we had the benefit, by the way, of the particular approach with the magnets. Like, we'd already built 3 of them at MIT. There'd been sort of like 50 to 100 built around the world. Based on the size and the complexity of them, we know how long they take to build, right? And we said, okay, if we can actually make this one, we think it'll take blank years to make this fundamental technology development, which is a superconducting magnet. Then it should take blank years to actually build the prototype, and then blank years to build the thing that goes on because we'd built them before. So we have that advantage. And we added those up in a very serious way. And we said, and this was 2018, we said we're 15 years. It's like, because it looks like that's how long it takes. And right now, we're almost exactly still on that timeline.
So that's a decade from now.
So that's a decade from now.
Okay.
But I would just caution everyone. So we're still on that pathway, and there's still challenges which are around on it. But at least we're making a try at it, right? And imagine now you have this isn't just for your own country. This can scale to actually power the world forever. And you have control not just of that particular design, but all of the things it takes to build it. It's like, so just imagine a future where I want to see one where we develop in a political system that actually that favors personal freedom and choices around these things, because in the end, it's going to be about people's well-being. That's why we want economic, clean energy sources. I'm not sure if we're going to win, but I think we will if we actually get our act together. That namely, and governments are reflections of the societies that we have. It's like, it almost goes back to my beginning comments. Like, we don't really know, first of all, how hard this is going to be about the energy transition. Like, Rob, you and I work in this every day. It's still hard to imagine the scale of this and how hard it is. But it's like, isn't this the thing worthy of trying, right? Tell me where there's a higher priority.
What if it works?
And then what if it works?
There we go.
Holy cow, right? And I think we should imagine a world where it works in all different kinds of ways. Yeah.
So in that world, there are going to be literally tens of thousands of fusion reactors if we continue down this path. What makes me worry is that that's really a deployment story. That's not an invention story and figuring out how to do it elegantly, which is what we're doing right now in our current in our current phase of commercialization. This deployment is something that the Chinese have done particularly well. We invented solar panels, they own the industry. We invented lithium-ion batteries, they own the industry. We get the first electric cars, they're going to own that too. So how do you think about that deployment and winning that race, not getting forced out of it? What are we going to have to do to build a global fusion industry in which we still play?
So we've got to figure out all kinds of things, right? It's a race in some sense between 2 different kinds of development systems. And the advantage, I would argue, that we have is that it primarily gets driven by markets, right? And then what happens is that companies come in and make products that actually that respond to the markets. So what is the market? It's about decarbonizing vast amounts of our energy sources as well too. So I think what it looks like is I am pretty sure it doesn't not look like a monolithic single design of a fusion device. And the reason for this is because energy itself, as you know, is a very complex market about what we actually use energy for. And fusion has this adaptability and flexibility that comes from its underlying science of those things I described before, that says there's all different kinds of ways to make a product that respond in the energy market. So I think what success looks like is actually multiple energy products. You have to get past the goalposts of the science requirements around it, obvious on that. But if you get to that place, then I believe like the invisible hand kind of wins, right? It's going to be that aspect of spurring on competition among different concepts and about how you respond in the energy market. So when you're coming up with a new product, go after a market that almost not necessarily doesn't exist, that has no other choices, right, around on that. And I think we have a real chance of doing that through these 40 companies, that are around. Not all of them are going to work, but if you come up with a handful of different kinds of concepts that can actually respond to the energy market, that's what success is going to look like. And I think that's why we can still, win that race. In fact, if you ask this question, if I was in front of a really wealthy person, I say, please work with me so that I understand, like, how did we get all these other amazing technologies? Because not repeating the mistakes of history, but also learning from the successes of these other sectors is, to me, a way that we can actually accelerate fusion across the board. And that's really where I personally feel really committed to learning about those aspects of it, but also then working along with my fusion colleagues to see about what we can actually deliver in the next decade. Because if we can deliver a few of them, like a few pilot plants in the next decade, we're changing, I think, our trajectory on clean energy.
A few pilot plants, meaning different technologies, just getting this stuff out there.
Dennis Whyte is professor in the Department of Nuclear Science and Engineering, former director of the MIT Plasma Science and Fusion Center. Dennis, thank you so much. This has been a great conversation.
Thank you.
Yeah, it's exciting to watch. Thanks, Dennis.
What If It Works is a production of the MIT Energy Initiative. If you like the show, please leave us a review or invite a friend to listen. And remember to subscribe on Apple Podcasts, Spotify, or wherever you get your podcasts. You can find an archive of every episode, all of our show notes, and a lot more at energy.mit.edu/podcasts. And you can learn more about the work of the Energy Initiative and the energy transition at energy.mit.edu. Our original podcast artwork is by Zeitler Design. Special thanks to all of the people at Mighty and MIT who make this show possible. I'm Kara Miller.
And I'm Rob Stoner.
Thanks for listening.